Hello, my name is Nitin B, and I'll be presenting a study on Turing machines and its applications. Turing machines were introduced by Alan Turing in the year 1936, and it has hence proved an important role in computer science and especially in theory of computation. From an aspect of automated theory, Turing machines have shed light on what algorithms computers can solve and what it cannot. Let us take a further look into Turing machines. As we can see from the Chomsky hierarchy, Turing machines take recursively enumerable language as an input language, along with other forms of grammar, such as linear bounded automation, pushdown automation, and finite automation. So, what are recursively enumerable languages? A recursively enumerable language is a formal language for which there exists a Turing machine that will halt and accept when presented with any string in the language as input, but may either halt and reject or loop forever when presented with a string not in the language. What is the difference between recursive and recursively enumerable languages? The main difference is that in recursively enumerable language, the machine halts for input strings which are in language L, but for input strings which are not in the language, it may halt or may not halt. When we come to recursive language, it will always halt whether it is accepted by the machine or not. Why is it called recursively enumerable? All recursive languages are also called recursively enumerable because you can just enumerate every string and then if it, output it if it's in your set. Recursive languages are also called decidable languages because you can decide for sure if an element is in it or not. Recursively enumerable languages are closed under the following operations. That is, if L and P are two recursively enumerable languages, then the following languages are recursively enumerable as well. The clean star, the concatenation, the union operation, and the intersection operation. Recursively enumerable languages are not closed under set difference or complementation. So what are Turing machines? A Turing machine is an abstract computational model that performs computations by reading and writing to an infinite tape. Turing machines provide a powerful computational model for solving problems in computer science and testing the limits of computation. It is worth pointing out that Turing machine is not a real machine. It's rather a mathematical model, a concept just like state machines, automata, or combinational logic. It exists purely in the abstract. An example of such an implementation is that Turing machine models are used to map the processes that occur within a CPU, which we shall discuss later. A Turing machine is defined by a 7-tuple set as follows, where Q is the finite set of states, T is the tape alphabet, B is a blank symbol, sigma is the input alphabet, delta is the transition function, Q0 is the initial state, and F is the set of final state. If any state of F is reached, input string is accepted. Let us consider an example of a Turing machine. We take the language L equal to 0 power n, 1 power n, where n is greater than or equal to 1. Here, as we can see from the table, Q is a set of Q0, Q1, Q2 and Q3, where Q0 is considered as the initial state. T is a set of 0, 1, x, y and b. Sigma is 0 and 1 and F is the set Q3, indicating that Q3 is the final set. So the working of Turing machine is as follows. Let us consider a string 0011. Initially, the head points to 0, which is underlined, and state is Q0, the initial state. The first transition function is delta Q0, 0 equal to Q1, x, r, which basically means that when 0 is encountered in the state Q0, it will move to state Q1, replace 0 by x, and the head will move towards the right. Moving further, when we take the transition function delta q1 comma 0 equal to q1 comma 0 comma r, which means that when state q1 is encountered by the element 0, it will remain in q1. It will not change the element 0, and head tape would move towards the right. Moving along further the string, the move will be delta q1 comma 1 equal to q2 comma y comma l, which means that it will move to q2 state and changing 1 to y. The head tape will move towards the left. Working on it in the same way, the machine would reach state q3 and head will point to B as shown below. If we take a non-deterministic Turing machine, there can be more than one possible move for a given state and tape symbol. But non-deterministic Turing machines does not add any power as compared to deterministic Turing machines. Every non-deterministic Turing machine can be converted into deterministic Turing machines. In multi-tape Turing machine, there can be more than one tape and corresponding head pointers, but even that does not add any power to the Turing machine. Every multi-tape Turing machine can be converted to a single-tape Turing machine. Here is shown the other examples. If we take a language with the constraint that the string must end with 101, the diagram for the transition function would be as shown below. Let us consider the application of Turing machines. It is often believed that Turing machines, unlike simpler automata, are as powerful as real machines and are able to execute any operation that a real program can. What is neglected in this statement is that because a real machine can only have a finite number of configurations, it is nothing but a finite state machine, whereas a Turing machine has an unlimited amount of storage space available for its computations. There can be a number of ways to explain why Turing machines are useful models of real computers. Uh, some of them are anything a real computer can compute, a Turing machine can also compute. The difference lies only with the ability of a Turing machine to manipulate an unbounded amount of data. However, given a finite amount of time, a Turing machine can only manipulate a finite amount of data. Like a Turing machine, a real machine can have its storage space enlarged as needed by acquiring more disks or other storage media. A practical example would be considering a Turing machine as an enumerator. An enumerator is a Turing machine with an output device attached to it. The language enumerated by the enumerator is a collection of strings it would print out. Example, if we take a language a power n, b power n such that n greater than or equal to 0, then the enumerator will output the following strings. The set of epsilon, ab, a square, b square, a cube, b cube, so on until infinity. Descriptions of real machine programs using simpler abstract models are often much more complex than descriptions using Turing machines. For example, a Turing machine describing an algorithm may have a few hundred states, while the equivalent deterministic finite automation on a real machine has quadrillions. This, make, this makes the DFA representation infeasible to analyze. Turing machines simplify the statement of algorithms. Algorithms running on Turing equivalent abstract machines are usually more general than their counterparts running on real machines because they have arbitrary precision data types available and never have to deal with unexpected conditions such as running out of memory. Thank you.